Okay, you've, you've learned in the previous grade that light goes through a transparent material and bends depending on the indices of refraction. Okay, so one of the properties that we're going to talk about when we talk about lenses is the refraction. So why? Because lens is an optical device which is used to bend light in a specific way. Okay. And with that, uh, refraction, it happens when light rays, okay, pass through a medium. Thus, it is bent. Or light rays may bend as they cross a boundary from one material to another, like from air to water. This bending of light rays is known as refraction, which means, class, that this is what we're going to look into, not just this explains rather why lens is connected to refraction. So here, uh, if you observe a straw, and when you look at you look at it directly on the bottom part, so you get to see that the straw looks like it is bent. When you lift it, it is straight. But when you put it back in the glass of water, it seems that it is bent. Okay? So the light rays from the straw are refracted or bent when they cross from water back into the air before reaching your eye. Okay? So that's how it is related. Now, when a light ray crosses from one material to another, the amount it bends depends on the difference in index of refraction between the two materials. So the refraction of light is governed by uh, Snell's law. Okay, let me write that again. So Snell's Snell apostrophe S law. So this was actually named after Dutch astronomer Willebrord Snell, wherein the the angle of incidence, the ratio of the angle of incidence and the angle of refraction is equal to the ratio is equal to the inverse of the sines of the angle of incidence and angle of refraction. We're not going to talk about the law, but basically what we've learned here that um, uh, it means that the light ray is bent as it passes through a medium. Okay? So you get to see a refraction from air into diamond. So when light ray pass through the air, that's what happens. Then when you have a diamond here, it passes through a diamond, light ray passes through a diamond, it is bent with the index refraction value of 2.42. This helps in determining if the diamond is real or not. For the refraction from air into water, okay, the index of refraction value of water is 1.33. So, if light is incident in a denser medium, it speeds up in another medium, okay, resulting to the bending away from the normal line. Now, to illustrate further, or to give you what we mean by index of refraction here, this is the ability of the material to bend rays of light And these are the values, the different values of the material, of the different values of a specific material. We have vacuum, the index of refraction is 1, so air is 1.001 to be exact. We have water, we have ice, we have glass, and we have um, the diamond. We used to calculate this, but because we don't have time anymore, okay, so we would simply like to present here that in Snell's law, if the index of refraction of medium is greater than that of another medium, then the angle of the first medium is still smaller of the two. So that's Snell's law. What this all means for lenses? Why do you need to know about this? So you have, suppose you have a glass lens in the air, glass lens in the air, then the lens has higher index of refraction than the air. So when the light ray enters the surface of the glass lens at an angle, so it bends towards the normal. It bends towards the normal. Okay? Then light goes through the other face of the lens back into the air. So in doing so, it bends away from the normal the moment it goes back. So to enable lenses to focus light and produce desirable images, the surfaces are curved, okay, in certain ways. Why? This is essentially what an optometrist does when uh, he or she prescribes a pair of eyeglasses. He or she determines the curvature of each side of the glass, the curvature of each side of the glass, okay? In order, why does it need, why does he need this? In order to bend light in the desirable way, okay? Now, refraction of light has a is applicable in some phenomena. Okay, a very good example of this is the mirage, an illusion caused by the refraction of light waves because light travels faster in warm air. So we have prism, okay, the triangular piece of glass that shows the bending of light. We have also dispersion, the separation of light into a spectrum by refraction, and we have rainbows. After a rainstorm passes, sunlight reflects in the many small raindrops. Okay. Furthermore, uh, when we talk about lenses, okay, we have to think its practical application. Okay. So, as what I have mentioned, lenses are essential for optometrists. Okay, because this is to correct eyesight, right? That's how it is. Or to give also comfort or adjustment on the image seen on the scene or produced by lens. So there are two kinds of lenses. We have the converging lens and diverging lens. Converging lens bends an incident ray. So we have here the incident ray parallel to the optical axis and toward the focal point. The diverging lens bends an incident ray, okay, parallel to the axis outward, away from the focal point. So that's it, away from the focal point. But if you connect it virtually, so it is on the uh, axis, it's on the incident ray. Okay, the point is on the incident ray. Now, let me clear that first. Okay, so A lens can form virtual image just a mirror does. Rays from the same point on an object are bent by the lens so that they appear to come along uh, much larger than the object. So just like the magnifying lens. Okay, so how is the lens formed here? So that's it. You have the refracted rays and forms a virtual image. Now, lens is, as what I've said, a basic optical device that uses refraction on two surfaces, okay, to produce an image, whether the image is real or virtual. Specifically, when we say thin lens, it's one whose thickness is small relative to its focal length, eh, to the radii of the curvature of its two surfaces, and to the object and image distances. There are two types of, as I've mentioned, okay? So converging lens, converging lens can also form a real image. So in a real image, light rays from the object actually come back together, okay? A lens that has two surfaces, each of which may be flat, concave, or convex. Whatever the shape there, the surfaces, there are two categories of lenses. Okay, so we have the converging and diverging. The converging lens are thicker, so thicker across the middle rather than the edges. That's converging. And sometimes it is known as positive lens or lenses. Okay, positive lenses happen there. Okay, it's easily recognizable again because the middle of the lens is thicker than the edges. So we have there double convex, plano convex, or converging meniscus. Sometimes this is also called biconvex. No? Now, uh, the most familiar here is the double convex lens. Okay, why? Where is this used? There, this is used in a simple magnifying glass. Okay, so converging lens, magnifying glass. On the other hand, diverging lenses are thicker on the edge, yes, than the middle, thicker on the edge than the middle. Light goes through the diverging lens, and due to the shape of its surfaces on either side of the lens, the refracted light rays are directed away from the principal axis. So you get to see an example here, double concave or biconcave. We have also the plano concave, and we have the diverging meniscus. So they are very easily recognizable because, again, the middle parts of the lenses are thinner than the edges. Now, just like spherical mirrors, lenses are also characterized by the number, okay, known as the focal length. If you, for those who ask an optometrician or an optometrist, okay, check if you allow the optometrist to check your eyes, the condition of your eyes, the optometrist will give you value like positive 1.75, negative 1.75. Okay. Now, how do these work? Diverging lenses have negative focal length. So take note. Negative focal length. Converging lenses have positive focal length. An optometrist diagnoses vision problems and prescribes eyeglasses. Again, if you have ever any need for eyeglasses, you might have noticed that the grade of your eyeglasses is written in decimals, 1.75 positive or negative. This grade is the power of each of your lenses. Okay, so actually, that is power of lens is equal to 1 over f. No need for us to calculate. That is to uh, explain how what does the grade mean. Grade is the power of each of your lenses. Now, therefore, how do lenses produce an image? So we have learned that a lens has two surfaces that bend light, right? So how does it produce an image? Okay, on the screen, okay, is the three ways for you to follow in order to describe the image. We will be using the ray diagram. This is very similar to mirror. It's just that the virtual and the real image is opposite than that of the lens. Okay? So a ray diagram is the best way to understand what type of image is formed by a lens and whether the image is magnified or inverted. These three rays follow the rules for how light rays are bent by the lens. Okay? A light ray passing through the center of the lens is not deflected at all. Okay? So what do you mean by that? Here is an example. So a light ray passing through the center is not deflected at all. So pardon my line. It's not that straight. Okay? So that's rule number one. A light ray parallel to the axis passes through the far, far focal point, which means to say the other side. So from here, parallel, just like in the mirror, in the middle, so it passes through a far focal point. Next, okay, the light ray passing through the near focal point emerges parallel to the axis. So what do we have here? Malabay siya, no? Sa focal point and then make a parallel line. So the intersecting lines is where the image is formed. Is that clear? So I think that's very familiar. Okay. So we have here converging lens bends the focal point and it produces a real image. Converging lens, it's inside the focal point. It produces also virtual and larger image. Diverging lens is anywhere so that it's producing only virtual and smaller than the object. Okay? So we're studying the mirrors and the lenses. We call them as optical systems. Collection of mirrors, lenses, prisms, and other optical elements that perform a useful function with light. So the characteristics of optical systems are where is the location, the type, and magnification of the image, the amount of light that is collected, the accuracy of the image in terms of sharpness, color, and dispersion, okay, and the ability to change the image like the telephoto lens on a camera. Now, the defects in the image is called aberration. Aberrations and can come in from several sources. Okay, so when we say chromatic aberration, it is caused by the dispersion when different colors focus at different distances from the lens. So you call that as chromatic chromatic aberration. Okay. There is also known as spherical aberration. What is this? This causes a blurry image. Okay. Blurry image because light rays farther from the axis focus to a different point than rays near the axis. So this is very common in camera, no? If hindi mo siya move ang lens properly. Okay? Now, let's go over on the applications of the lenses. Okay? I hope that you get to see that. One of which is in the telescope. What do you see in the telescope? You have the lens, you have the objective eyepiece. Okay? So we have also another objective eyepiece, and that's how it looks like. And it's made up of these two lenses, the telescope. Okay? So concave lenses are also called diverging lenses, while convex lenses bulge in the center is also known as converging lenses. So here are the uses of convex lenses. We have the eye, spectacles for long sight, camera lens, and magnifying lens. Okay, so you're familiar. What about the convex lens? Let me go back to that. Okay, so uses of concave lenses include glasses for nearsightedness. Glasses for nearsightedness. Okay, so there are also cases that lenses, there are multiple uses. A particular object uses multiple lenses. So image from lens 1 becomes a object for lens 2, and lens 1 creates a real, inverted, and enlarged image, but in lens 2, it creates a real, inverted, and reduced image. And the combination gives us real upright, but enlarged and the image of the object. Okay? So, practical application, the hypermetropia and the myopia. Okay? So, in uncorrected hyperopia, the image of the object falls behind the retina. In uncorrected myopia, the image falls in front of retina. The purpose of convex lens is to bring the image forward, while the purpose of concave lens is to bring the image behind. Okay? So, if the correcting lens itself is moved upward, okay, is moved upward, then move forward, the image will move still forward. Okay? Take note of that. So these are the vision problems, no? And it can be corrected. So we have the hypermetropia or hyperopia. The other term for this is hyperopia. We have myopia. Now, what is hyperopia? Hyperopia, I'm thinking of, this is to correct farsightedness, okay? While myopia is the medical term for nearsightedness. So nearsightedness. Okay. So the purpose of the concave lens to bring the image. So people suffering from visual problems can see close objects clearly, but distant objects are blurry. Okay. So that's it. What about the one with doble vista? That's for people, many people aged 40 and above suffer presbyopia. Presbyopia. Okay? Na bala ang, if this is the glass, no? This is normal, diriya for reading. Okay? So, bifocal lens na siya, bifocal lens. And then, of course, there is such thing as astigmatism. Okay? This one cannot focus the horizontal and vertical lines. Okay? So, they prefer to wear contact lenses instead of eyeglasses. Okay? The latter being inconvenient to use. So, that's about lenses and practical applications. Now, something for you to remember. Okay? So, I give you here the mnemonic. Zir, dove. Or, what do we have? What does zir dove mean? Okay? This is, comes before D. This is converge, inverted, and real. So, inverted and real. While diverge means upright and virtual. So please remember that mnemonic. This will help you in differentiating uh, diverging lens from a converging lens. So when we say converge, it is convex lens, but it is concave mirror. When we say diverge, it is concave lens, but concave mirror. Okay? Familiarize that one. Now we move on to a ray diagram. This is just quick because you're familiar with this already. What type of lens do you see? Okay, so it's a convex lens. So when we do the ray diagramming, it will pass through the vertex, the central point. Okay, then parallel one, second diagram will be parallel to the x-axis, then it will pass through the focal point there. Far focal point. Then the next, it will pass through the focal point, draw a line, and then that will pass through a focal point, and then draw a parallel axis. That is where the image is. Okay? That is where the image is. Now, what do you produce here? That is real image. Okay? Enlarge, is it enlarge? Okay, a little bit enlarged, right? So convex lenses and real images. Paper can be ignited by producing, that's how to show that it merge. Okay, it merge at the focal point, it intersects. That is a good example. So again, after being refracted by the lens, the rays converge at the focal point. The figure shows two focal points on each side, one on each side of the lens. You could not turn the lens around. It will still, I mean, if you could turn the lens around, it will still work the same. Now, let's have the first case. What if the object is at infinity, very, very far? What do you see? What image will be produced? The image is real and it's found in the focal point. It's on point and located at the focal point. Okay, very much located at the focal point. One moment, please. And then what? On the opposite side of the lens. Okay, so that if the image is infinite, is at infinity. So what does it produce? Real, inverted, diminished, and the image is at real focus. Now, meaning to say the image is at focus. Huh? Now, the second case, what do you see? So again, mapass through, dira, then parallel line to the vertex, and then passes through the focal point. Where the two lines intersect is where the image is produced. So this is condition means the object is beyond 2f, farther away from the curvature or 2f. The image is what? Real, inverted, and that's diminished. Okay? It can be found between F and 2F on the opposite side of the lens, F and 2F. Again, it's smaller than the object. Okay? So what's the case? The case is when the object is found beyond 2F. Third case. The third case is if the object is at 2F. Ara, yun siya sa 2F. Okay? So what do we produce? Real, inverted, same size. Located at 2F, the image is also located at 2F. So kung ari di, ang case 3 is, the object at 2F, ang image na ara man na sa 2F. On the opposite side of the lens. Okay? Next. Clear. Let's clear this. Object between F and 2F. Siya between F and 2F. What will you produce here? Real, inverted, located beyond 2F, again, opposite side, and you have a magnified object. Okay? Na magnify ang object. Next case. Next case. Here. So, malabay sa center, parallel to the optical axis, and then malabay sa focal point. This happens if the object is at F. So whether you draw a vertical line there, straight mo na, no image is formed. Okay? Next. Next. What if the object is between F and the lens? F and the lens. Okay? The vertex, right? You know that it's the vertex. So what do we get? So here, this will pass through the focal point, or I mean, it will pass through the center rather of the vertex, then parallel to the focal point. Now, you do not see an image, you try to extend. This is what you get, remember? So the intersecting line is where the image is produced. Therefore, it is virtual upright on the same side of the lens and magnified. Okay? So please take note, when does a converging lens produce virtual image? If the object is between F and the lens. Okay? Next case. Oh, sorry. I mean, here are the practical applications. If the object distance is at infinity, uses of that is telescope. If the object is within the curvature, these are the applications, camera and eye. If the object is found at the curvature, so inverted, same size and real. That's why your photocopier works exactly of the same size. Okay. So if the object is between F and 2F, that's the image produced in the projector. If the object is at F, so no image is formed. Therefore, a good example of that is spotlight. If the object is found upright, I mean between F and the lens, therefore it is magnified, upright, and virtual. So it's a magnifying glass. Okay, that's a convex lens. Now, what about concave lens? There is no problem with not so much with concave lens because ang concave lens amo lang din nang i-produce siya. Okay? So concave lens is a concave lens causes all rays to diverge. The figure shows how such lens forms virtual image. So the image is located at the point from where the two rays apparently diverge. Okay. So let's see how it works. Balikan ko ha. Okay. So ray 1 is from Don't forget to write the vertex line so that that's where you stop. From the top of the image, parallel, okay? So you draw, it will pass through the focal point. Therefore, you draw, or using your ruler, you draw straight line, okay? Next, so it will pass us through the focal point. From here to the focal point, but of course, where this meets, you make intersecting lines. You make a line there, okay, where it meets. Thus, this is where the image is seen. Okay. So, what type of image? It is upright, smaller in size, and same with the object. Okay. So that is very simple for concave lens. There are no more and no more what you call this for concave lens. The case is just simply, let me go back. For concave lens, the case is just simply one. One case lang din na siya, and that is what? The image form is virtual. Virtual lang din na siya. Okay? When the object is the image is always virtual. What else? Upright, right? And of course, diminished or reduced. It is on the same side of the lens as the object. Same side of the lens is where the object is. Okay? The position of the object affects only the image size and distance from the lens, but not the nature of the image. So this is a concave lens. Okay? So I hope you've learned from the discussion.